Let's start with something that sounds impossible. At one point, very early in its life, the universe expanded faster than the speed of light. Way faster, actually. Regions of space that are now billions of light years apart were once so close together they could have been touching, and they flew apart at speeds that make light look like it's standing still. And here's the thing that didn't break any law of physics. Not one. Not even a little bit. The cosmic speed limit stayed perfectly intact the entire time. Now, if you've ever heard that nothing can travel faster than light, that probably sounds like a contradiction. And honestly, it should, because the way most of us learn about the speed of light, we're taught it as this absolute, unbreakable barrier. Einstein said so. It's baked into special relativity. Nothing with mass can reach the speed of light, let alone exceed it. And yet, the universe did something that seems to violate exactly that principle, right at the beginning of time, and physicists will tell you with a straight face that no rule was broken. So how does that work? How can something expand faster than light without breaking the speed of light? That's what we're going to talk about tonight. And the answer, I promise you, is more beautiful and strange than you'd expect. It touches on the deepest questions we can ask about the nature of space, time, and reality itself. It involves the very first fraction of a second after the Big Bang, the curvature of the cosmos, the reason the night sky looks the way it does, and one physicist's late-night moment of clarity that changed everything we thought we knew about the beginning of everything. But let's not rush. Let's start where it makes sense to start, with the speed of light itself and what Einstein actually said about it. Because it turns out, the rule isn't quite what most people think it is, and understanding what the speed of light really means, what it actually forbids and what it doesn't, is the key to unlocking this whole puzzle. So here you are, lying in the dark, maybe staring at the ceiling or maybe already closing your eyes. And somewhere nearby, there's probably a light source, a lamp, the glow from a phone screen, maybe a nightlight. Whatever it is, photons are reaching your eyes right now, and each one of them is traveling at about 300 million meters per second. That's roughly 186,000 miles per second, if you prefer. Fast enough to circle the entire Earth about 7.5 times in a single second. Fast enough to get from the Earth to the Moon in a little over 1 second. Fast enough to cross from the Sun to the Earth in about 8 minutes. That speed, which physicists call c, is one of the most fundamental constants in all of physics. It shows up everywhere, not just in optics, not just in how light behaves, but in the deep structure of the equations that govern how the universe works. It appears in Einstein's famous equation, E equals mc squared. It sets the relationship between energy and mass. It's woven into the fabric of space-time itself. And Einstein's special theory of relativity, published in 1905 when he was just 26 years old, established something remarkable about this speed. No object with mass can be accelerated to the speed of light. The closer you get to it, the more energy it takes to go faster. And as you approach the speed of light, the energy required approaches infinity. You'd need an infinite amount of energy to push even a single electron up to that speed. It's not a practical limitation, like saying you can't build a car that fast. It's a fundamental limitation, built into the geometry of space-time. But here's where it gets subtle, and this is the part that most popular explanations gloss over. Einstein's speed limit applies to objects moving through space. It says that no object, no particle, no signal, no piece of information can travel through space faster than light. That's the rule. Through space. Those two words matter more than almost anything else in this entire story. Because space itself, space isn't bound by that rule. Space can do whatever it wants. Space can stretch, expand, warp, compress, ripple, and yes, it can expand so fast that 2 points embedded in it are receding from each other faster than light. And nothing about that violates Einstein's equations. In fact, Einstein's own theory of general relativity, his bigger, more complete theory of gravity, published in 1915, explicitly allows for it. Not as some exotic edge case, but as a natural, expected behavior of the cosmos. Think about that for a second. The same physicist who gave us the speed limit also gave us the theory that says the speed limit doesn't apply to space itself. That's not a contradiction. It's just that the universe is more nuanced than the one-sentence version of the rule. Now, to really appreciate what this means, to feel it and not just hear the words, we need an analogy. And the classic one is pretty good, so let's use it. Imagine you've got a rubber band, a really long one, and you've drawn 2 dots on it with a marker, let's say a red dot and a blue dot, about an inch apart. Now imagine you grab both ends of the rubber band and you start stretching it. As the rubber stretches, those 2 dots move apart. Not because they're crawling along the rubber, not because anything is pushing them through the material, but because the material itself is expanding between them. Now here's the key part. If you stretch that rubber band fast enough, the red dot and the blue dot can be moving apart faster than any ant could crawl along the surface of the rubber. An ant on that rubber, trying to walk from the red dot to the blue dot, has a maximum speed. That's the ant's speed limit. But the dots can separate faster than the ant's speed limit, because they're not moving through the rubber. They're being carried apart by the stretching of the rubber itself. That's essentially what happens with the expansion of the universe. Galaxies, stars, planets, all of it. They're like dots on the rubber band. They're not flying through space, away from each other at incredible speeds. Space itself is stretching between them, carrying them apart. And the speed limit, set by the speed of light, applies to things moving through space, not to the expansion of space itself. And this isn't some obscure technicality. It's happening right now, tonight. As you lie here, space is expanding. Every bit of space between the galaxies is getting a tiny bit bigger, moment by moment. And for galaxies that are very, very far away from us, the cumulative effect of all that stretching means they're receding from us faster than the speed of light. There are galaxies right now whose light will never reach us, not because they're moving too fast through space, but because the space between us and them is expanding too quickly for even light to cross the gap. Makes sense so far, right? But here's where the story deepens, because what I just described, the expansion of the universe, is something that's happening gently today. Space is stretching, but slowly. The rate is measurable, and it's actually pretty modest when you look at the distances between nearby galaxies. What happened in the very early universe was something far more dramatic, something so extreme that it makes today's expansion look like a sleeping cat compared to a supernova. In the first fraction of a second after the Big Bang, the universe underwent a period of expansion so violent, so rapid, so incomprehensibly fast that it's hard to find words for it. In a time span shorter than you could possibly imagine, the universe expanded by a factor of at least 10 to the 26th power. Some models say more. That's a 1, followed by 26 zeros. The observable universe, everything we can see with our most powerful telescopes, all of it may have started smaller than a proton, and in less than a trillionth of a trillionth of a trillionth of a second, it ballooned to something the size of a grapefruit or a basketball, or depending on the model, maybe much bigger. That period is called inflation, cosmic inflation, and it's one of the most important ideas in all of modern cosmology. It explains things about the universe that nothing else can explain. It answers questions that the standard Big Bang theory, on its own, couldn't touch. And it does it all without breaking Einstein's speed limit, because it's not about things moving through space. It's about space itself expanding. But we're getting ahead of ourselves. To really understand inflation, why physicists dreamed it up in the first place, and why they're so confident it happened, we need to take a step back and talk about the Big Bang itself, what we actually know about the birth of the universe, and what strange clues led one young physicist in 1979 to a revelation that changed cosmology forever. So let's go there. Let's talk about how we figured out the universe had a beginning in the first place. Because that story, all by itself, is one of the great intellectual adventures in human history. For most of recorded civilization, humans assumed the universe was eternal. It had always been here. It would always be here. The stars were fixed. The cosmos was unchanging. Even Newton, who figured out the laws of motion and gravity in the late 1600s, pictured a static universe, an infinite, unchanging backdrop against which the drama of physics played out. The idea that the universe could have a birthday, that it could have burst into existence at some particular moment, would have struck most people before the 20th century as almost absurd. But then a few things happened, and they happened fast. In 1915, Einstein published his general theory of relativity, and this was a completely different beast from his special relativity of 1905. Special relativity was about objects moving at constant speeds in flat space. General relativity was about gravity, and Einstein's insight was breathtaking. Gravity isn't a force pulling things together. It's the curvature of space-time itself. Massive objects like stars and planets bend the fabric of space and time around them, and other objects moving through that curved space-time follow paths that look, to us, like they're being pulled by a force. But there is no force. There's just geometry. Curved geometry. Now, when Einstein worked out the math of general relativity, his equations described how mass and energy curve space-time. And here's the thing that startled even him. Those equations didn't naturally produce a static universe. They produced a universe that was either expanding or contracting. The math said space should be in motion. It should be getting bigger or getting smaller. It couldn't just sit there. Einstein didn't like that. It contradicted everything he believed about the cosmos. So he did something unusual. He added a term to his equations, a fudge factor, basically, called the cosmological constant. Its only purpose was to hold the universe still, to balance the tendency of space to expand or collapse. He set it to exactly the value needed to produce a static cosmos. It was elegant in a way, but it was also, as Einstein himself would later admit, a mistake. Perhaps the biggest mistake of his career, he once said. Because the universe isn't static. It really is expanding. The first person to seriously argue this wasn't Einstein. It was a Belgian priest and physicist named Georges Lemaitre, and his story is one of those quiet tragedies of science where someone is right before the world is ready to hear it. Lemaitre was a fascinating figure. Born in 1894 in Charleroi, Belgium, he'd served as an artillery officer in World War I, seen the horrors of the front lines, and then after the war, decided to pursue both physics and theology. He studied at Cambridge, at MIT, and at Harvard. He read Einstein's general relativity equations carefully, and in 1927, he published a paper arguing that the universe was expanding. Not just that it could expand, but that it was expanding. He even derived what we now call Hubble's law, the relationship between a galaxy's distance and how fast it's moving away from us, 2 years before Edwin Hubble himself published similar observations. But Lemaitre published his paper in a relatively obscure Belgian journal, in French, and almost nobody noticed. Einstein himself, when Lemaitre met him at a conference and explained his results, reportedly said something like, "Your calculations are correct, but your physics is abominable." Einstein just couldn't accept an expanding universe, not yet. Then came Hubble. Edwin Hubble was an American astronomer working at the Mount Wilson Observatory in California, perched up in the mountains above Los Angeles, using what was at the time the most powerful telescope in the world, the 100-inch Hooker telescope. And in 1929, Hubble published observations that changed everything. What Hubble found was this: virtually every galaxy he could observe was moving away from us. And not just moving away, but moving away at speeds that increased with distance. The farther away a galaxy was, the faster it was receding. This wasn't a random pattern. It was systematic, consistent, universal. How did he know they were moving away? Through something called redshift. And this is worth understanding, because it's one of the most important measurement tools in all of astronomy. You know how when an ambulance drives toward you, the siren sounds higher pitched, and when it drives away, the pitch drops? That's the Doppler effect for sound. The same thing happens with light. When a light source moves toward you, its light gets compressed to shorter wavelengths, shifting toward the blue end of the spectrum. When it moves away, the light gets stretched to longer wavelengths, shifting toward the red end. Redshift. Hubble measured the light from distant galaxies and found that almost all of them were redshifted. They were all moving away from us. And the ones farther away had more redshift, meaning they were moving away faster. He plotted distance versus recession speed and got a straight line. That line, that relationship, is Hubble's law. The slope of that line is called the Hubble constant, and measuring its exact value has been one of the great ongoing projects of modern cosmology. Now, here's something crucial about this expansion that a lot of people get wrong. It's not that galaxies are flying outward from some central point, like debris from an explosion. There is no center. The expansion is happening everywhere, equally, at every point in space. Every galaxy sees every other galaxy moving away from it. If you were sitting in a galaxy 1 billion light-years from here, you'd see our Milky Way moving away from you, and you'd see galaxies on the other side of you also moving away. Everyone thinks they're at the center. Nobody is. The rubber band analogy works here too. Every dot on the rubber band sees every other dot moving away from it as the rubber stretches. There's no special dot, no privileged position. The stretching is a property of the rubber itself, not of any particular point on it. So by the early 1930s, the observational evidence was clear. The universe is expanding, and Lemaitre took this to its logical conclusion. If the universe is expanding now, then at some point in the past, it must have been smaller, much smaller. And if you rewind far enough, everything in the observable universe must have been compressed into an incredibly tiny, incredibly hot, incredibly dense state. Lemaitre called this the primeval atom, or the cosmic egg. It was the first serious scientific proposal for what we now call the Big Bang. The term Big Bang itself, by the way, was coined as an insult. The British astronomer Fred Hoyle, who championed a competing theory called the steady-state model, where the universe had no beginning and no end, used the phrase Big Bang on a BBC radio broadcast in 1949 as a dismissive term. He was essentially saying, "Oh, so you think everything just started with a Big Bang? How ridiculous." But the name stuck, and Hoyle's preferred model eventually fell apart when the evidence piled up overwhelmingly in favor of a hot, dense beginning. And the most spectacular piece of that evidence came in 1964, almost by accident. Two radio astronomers at Bell Labs in New Jersey, Arno Penzias and Robert Wilson, were working with a large horn-shaped antenna, trying to detect radio signals bounced off satellite balloons. They kept picking up a persistent, annoying background hiss. They couldn't get rid of it. They tried everything. They pointed the antenna in different directions. The hiss was everywhere. They even cleaned pigeon droppings out of the antenna, thinking that might be the problem. Nope. The hiss was still there. What Penzias and Wilson had stumbled onto, almost without realizing it, was the cosmic microwave background radiation. The afterglow of the Big Bang, light that had been traveling through the universe for over 13 billion years, stretched by the expansion of space from its original scorching temperature down to just a few degrees above absolute zero. It's everywhere, in every direction, filling all of space, and it's one of the strongest pieces of evidence we have that the universe began in a hot, dense state and has been expanding and cooling ever since. Think about that. You can literally detect the leftover heat from the birth of the universe. It's faint, just a whisper of microwave radiation, but it's real, it's measurable, and it's all around you right now. Some of it is passing through this room as you lie here. A tiny fraction of the static you'd see on an old television set, back when TVs had rabbit ear antennas, was actually this primordial light. The birth cry of the cosmos, scattered across your TV screen. Penzias and Wilson won the Nobel Prize for their discovery, by the way, which is remarkable when you consider that they weren't even looking for it. They were trying to do something completely different. But that's how science works sometimes. You find the thing you weren't looking for, and it turns out to be the most important discovery of your career. So by the late 1960s, the picture was coming together. The universe began in a hot, dense state. It has been expanding ever since. The cosmic microwave background is the leftover glow from that early epoch. This is the Big Bang theory, and it's one of the most successful and well-supported theories in all of science. But here's the thing, and this is where our real story begins. Despite all its success, the standard Big Bang theory had some serious problems. Not contradictions with the data, exactly, but puzzles. Deeply strange coincidences that the theory couldn't explain. Things that seemed to require either incredible fine-tuning or some missing piece of the puzzle. And it was these puzzles, these nagging "but why" questions, that led to the idea of inflation. Let me tell you about the first and most famous of these puzzles. It's called the horizon problem, and once you understand it, you'll see why it drove physicists a little bit crazy. Remember the cosmic microwave background, that leftover glow from the Big Bang? Well, when scientists measured it carefully, they found something astonishing. It was almost perfectly uniform. The temperature of this radiation is about 2.725 degrees above absolute zero, and it's the same in every direction, to an accuracy of about 1 part in 100,000. That's like measuring the temperature of the ocean across the entire planet and finding it the same everywhere to within 1,000th of a degree. It's absurdly uniform. Now, you might think that's not surprising. If everything started from the same hot, dense point, of course it would all be the same temperature, right? Like a pot of water that's been well stirred. Everything should be uniform. But here's where it gets strange. For things to reach the same temperature, they need to have been in contact with each other. They need to have had time to exchange energy, to equalize. Think about it. If you put a hot cup of coffee and a cold glass of water in the same room, they'll eventually reach the same temperature, but only because heat can flow between them. If you put them in separate, sealed, insulated boxes with no connection between them, they'd stay at different temperatures forever. Equalization requires contact, communication, exchange, and in the standard Big Bang model, The regions of the universe that are now on opposite sides of the sky were never in contact. They couldn't have been. They were too far apart, and there simply wasn't enough time since the Big Bang for light, or anything else, to travel from one to the other. Light is the fastest thing there is, and even light couldn't have made the journey. Let me put some numbers on this to make it concrete. The cosmic microwave background was emitted about 380,000 years after the Big Bang, when the universe had cooled enough for atoms to form and light to travel freely. At that time, the observable universe was much smaller than it is now, but still enormous. And the maximum distance that light could have traveled in 380,000 years is, well, 380,000 light years. That's the horizon at that time. Anything farther apart than that had no way of communicating, no way of exchanging energy, no way of reaching the same temperature. But regions that are now on opposite sides of our sky, regions whose cosmic microwave background we can measure, were much farther apart than 380,000 light-years when that light was emitted. They were separated by tens of millions of light-years. They were far beyond each other's horizons. They had no causal connection whatsoever. And yet they're at exactly the same temperature. How? Why? In the standard Big Bang model, there's no explanation. It's just a coincidence. The universe just happened to start out perfectly uniform everywhere. But physicists don't like coincidences. Especially not coincidences that require conditions to be fine-tuned to 1 part in 100,000 across regions that had no way of coordinating with each other. That's the horizon problem. And it's not a minor quibble. It's a deep, fundamental puzzle about the initial conditions of the universe. Why was the early universe so uniform when there was no physical mechanism for it to become that way? Now let me tell you about the second big puzzle. It's called the flatness problem, and it's just as strange. When we talk about the shape of the universe, we're not talking about whether it's round or square. We're talking about its geometry, its curvature. General relativity tells us that the distribution of mass and energy in the universe determines the curvature of space. And there are 3 possibilities. The universe could be positively curved, like the surface of a sphere, where parallel lines eventually converge. It could be negatively curved, like a saddle, where parallel lines diverge. Or it could be flat, where parallel lines stay parallel forever, just like the geometry you learned in school. Observations tell us that the universe is very, very close to flat. Not exactly, perfectly flat, maybe, but extraordinarily close. The geometry of the universe, as best we can measure it, is flat to within about 0.5%. Now here's why that's strange. In the standard Big Bang model, a flat universe is an unstable condition. It's like balancing a pencil on its tip. If the universe starts out even slightly curved in either direction, that curvature amplifies over time. A universe that's even a tiny bit positively curved at the beginning will become more and more positively curved, eventually collapsing back on itself. A universe that's even a tiny bit negatively curved will become more and more negatively curved, expanding into a cold, empty void. Flatness is the knife's edge between these 2 outcomes. For the universe to be as flat as we observe it today, 13.8 billion years after the Big Bang, it had to be flat at the beginning, to an almost absurd degree of precision. At 1 second after the Big Bang, the curvature had to be tuned to within 1 part in 10 to the 15th. That's 1 part in 1,000 trillion. At the Planck time, the earliest moment physics can describe, the tuning had to be even more extreme, something like 1 part in 10 to the 62nd power. That's not a coincidence. That's a conspiracy. The universe had to start out balanced on the most impossibly sharp knife's edge imaginable, and then stay balanced for billions of years. and the standard Big Bang theory has no explanation for why. It just says, well, those were the initial conditions. Deal with it. But physicists don't deal well with unexplained fine-tuning. When something requires conditions to be set to 1 part in 10 to the 62nd power, that's a giant flashing sign saying, you're missing something. There's a mechanism you don't know about. Some piece of the puzzle is hidden. And there was a third problem too, sometimes called the magnetic monopole problem. Grand unified theories of particle physics, the theories that try to combine the electromagnetic, weak, and strong forces into one framework, predict that the extremely high energies of the early universe should have produced huge numbers of magnetic monopoles, hypothetical particles that carry a single magnetic pole, either north or south, but not both. These particles should be incredibly massive and incredibly stable, and yet we've never found a single one. Despite decades of searching, not one magnetic monopole has ever been detected. If the early universe produced them by the truckload, as the theories predict, where did they all go? 3 problems. 3 deep, stubborn mysteries. The horizon problem, the flatness problem, the monopole problem, and the standard Big Bang theory, despite all its successes, had nothing to say about any of them. Until one evening in December 1979, when a young physicist at Stanford had an idea that changed everything. His name was Alan Guth, and in 1979, he was not exactly a star of the physics world. He was 32 years old, bouncing between postdoctoral positions, not yet having landed a permanent faculty job. He was working on problems in particle physics, specifically on magnetic monopoles and grand unified theories, at the Stanford Linear Accelerator Center, known as SLAC. He was smart, clearly, but he hadn't yet made the kind of breakthrough that turns a career into a legend. Guth had been thinking about the monopole problem. He was attending a talk by a fellow physicist named Robert Dicke, who was discussing the flatness problem, and something clicked. Guth started wondering, what if there was a period in the very early universe when space expanded exponentially, not just fast, but exponentially, doubling in size over and over again in unimaginably rapid succession? He went home and started working through the math. And on the evening of December 6, 1979, he realized something extraordinary. If the universe had undergone a brief period of incredibly rapid, exponential expansion very early in its history, it would solve the flatness problem, it would solve the horizon problem, and it would solve the monopole problem. All 3. With one idea, he wrote in his notebook that night, in capital letters, underlined twice, "Spectacular realization," and beneath it, he sketched out the bones of the idea that would become cosmic inflation. Let me tell you what he figured out, because it's genuinely beautiful in its elegance. Start with the horizon problem. The reason distant regions of the cosmic microwave background are at the same temperature, even though they're too far apart to have ever been in contact, is that they were in contact, before inflation, before the exponential expansion. In the very earliest moments of the universe, these regions that are now on opposite sides of the sky were crammed together in a tiny patch of space, close enough to equalize their temperatures, close enough to exchange energy and reach thermal equilibrium. They had time to talk to each other, to become uniform. And then inflation happened. That tiny, uniform patch was blasted outward, expanded by a factor of at least 10 to the 26th power in a fraction of a second. The regions that had been neighbors were flung to opposite sides of the observable universe. But they still carried the memory of their earlier contact. They were still at the same temperature, because they'd had time to equalize before inflation stretched them apart. It's like taking a small bowl of perfectly mixed soup and then magically stretching it to the size of the Pacific Ocean. Every part of that ocean-sized soup would be at the same temperature, the same consistency, the same composition, because it was all mixed together when it was small. The uniformity was established first, and then the expansion happened. The horizon problem dissolves. Now the flatness problem. Why is the universe so close to flat? Because inflation makes it flat. Think about the surface of a balloon. When the balloon is small, you can see its curvature clearly. The surface bends. But now imagine blowing that balloon up to the size of the Earth, or the size of the Sun, or the size of a galaxy. The bigger the balloon gets, the flatter any small patch of its surface appears. Stand on a patch of a galaxy-sized balloon and you'd never be able to detect the curvature. It would look perfectly flat in every direction. That's what inflation does to the universe. Whatever curvature the universe started with, positive or negative, inflation expanded space so dramatically that any curvature was stretched out to the point of being undetectable. The universe became flat, or at least so close to flat that we can't measure any deviation. The fine-tuning problem goes away, because you don't need to start with a flat universe. You just need inflation to make it flat after the fact. And the monopole problem? Inflation solves that too. If magnetic monopoles were produced in the very early universe, before inflation, then inflation diluted them. It took whatever density of monopoles existed and spread it out across an exponentially larger volume. The monopoles didn't disappear. They just got spread so thin that you'd expect maybe one in the entire observable universe, maybe none, which is exactly what we observe. 3 problems, 1 solution: inflation. Now, you might be wondering what actually drove this exponential expansion. What powered it? And this is where things get really interesting, because the answer involves a concept that sounds almost paradoxical: a field with negative pressure. In ordinary physics, pressure pushes outward. The air in a balloon pushes against the walls. But general relativity tells us that both energy and pressure contribute to gravity. And here's the thing that Einstein's equations reveal: positive pressure actually contributes to gravitational attraction. It pulls things together. But negative pressure, pressure that pulls inward rather than pushing outward, that creates gravitational repulsion. It pushes things apart. And Guth proposed that in the very early universe, there was a quantum field, which he called the inflaton field, with an N, not to be confused with inflation itself, that was temporarily stuck in a high-energy state. This state had positive energy density, but negative pressure. And according to general relativity, that combination creates a repulsive gravitational effect that drives exponential expansion. It's counterintuitive, I know. We're used to thinking of gravity as something that pulls, but Einstein's equations are clear. Under the right conditions, gravity can push. And if the conditions are extreme enough, it can push violently, driving space apart at an exponential rate. The inflaton field, in this picture, is like a ball sitting at the top of a hill. It's in an unstable, high-energy state. It wants to roll down the hill to its lowest energy state, its ground state. But for a brief period, something keeps it up there. Maybe the hill is very flat at the top, or maybe there's a shallow valley or plateau near the summit. Whatever the reason, the field lingers in that high-energy state long enough for inflation to happen. And while it lingers, the universe expands exponentially, doubles in size, then doubles again, over and over, many dozens of times. Each doubling happens in an incredibly short time, perhaps around 10 to the minus 37 seconds. And after maybe 60 to 70 doublings, give or take, the field finally rolls down the hill, reaches its ground state, and inflation ends. The energy stored in the inflaton field gets dumped into the universe as a flood of particles and radiation, reheating the cosmos and kickstarting what we think of as the normal, hot Big Bang. That transition, from the inflationary phase to the normal expansion, is sometimes called the graceful exit. And getting the graceful exit right was actually one of the trickiest parts of the theory. Guth's original version of inflation, which he published in 1981, had a problem with this. The inflation ended too abruptly in some regions, and not at all in others, creating a chaotic mess of bubbles that didn't match the smooth universe we observe. It was a beautiful idea with a fatal flaw, but within a year or two, other physicists found a fix. In 1981 and 1982, Andrei Linde in the Soviet Union and, independently, Andreas Albrecht and Paul Steinhardt in the United States came up with what's called new inflation, or slow-roll inflation. In their version, the inflaton field doesn't get stuck in a false vacuum and then tunnel out, like Guth proposed. Instead, it rolls slowly down a very gentle slope, taking its time, generating a smooth, extended period of exponential expansion before gradually coming to rest. This solved the graceful exit problem and gave a version of inflation that matched observations beautifully. Andrei Linde, in particular, became one of the most influential cosmologists of the late 20th century. He was a Soviet physicist working at the Lebedev Physical Institute in Moscow when he developed his version of inflation. He later moved to Stanford, where he continued to push the theory forward. Linde was known for his infectious enthusiasm and his willingness to follow ideas wherever they led, even when they led to places that made other physicists uncomfortable, like the multiverse. But we'll come back to that. So let's step back and appreciate what inflation actually says happened in the first moments of the universe, because the timeline is staggering. The Big Bang happens. Time begins. For the first tiny fraction of a second, physics at the Planck scale, the most extreme conditions imaginable, conditions we don't have the physics to describe yet. Then, at about 10 to the minus 36 seconds after the beginning, give or take, the inflaton field is in its high energy state, and inflation begins. Exponential expansion kicks in. Space doubles in size every 10 to the minus 37 seconds or so. By the time inflation ends, at about 10 to the minus 32 seconds after the Big Bang, so we're still talking about an almost inconceivably short period of time, a trillionth of a trillionth of a trillionth of a second, the universe has expanded by a factor of at least 10 to the 26. Some models say 10 to the 50 or more. A region smaller than a proton has been stretched to a size larger than the current observable universe. Let that sink in. In less time than it takes a photon to cross the diameter of a single atom, the universe went from subatomic to cosmic. And during all of this, the expansion was genuinely faster than light, in the sense that the distance between any 2 points embedded in this space was increasing faster than light could have traveled between them. But nothing was moving through space faster than light. Space itself was doing the expanding. The speed limit, Einstein's speed limit, was never violated. It simply doesn't apply to the stretching of space. This is the answer to our central question, really. The universe expanded faster than light and didn't break a single law because the speed of light limits motion through space, not the expansion of space. And inflation, the mechanism that drove this expansion, is a completely natural consequence of general relativity combined with quantum field theory. There's no magic, no hand-waving, just the equations of physics, doing exactly what they say they'll do under those conditions. But I don't want to just give you the answer and call it a night. Because the really beautiful stuff is in the details. Let's go deeper. Let's talk about the evidence for inflation, how we know it actually happened, and what it tells us about the universe we live in. Because here's the thing, Inflation isn't just a clever mathematical trick that solves three problems. It makes predictions, specific, testable predictions, that we can check against observations. And the fact that these predictions have been confirmed over and over by increasingly precise measurements is why most cosmologists today believe inflation really happened. The most important of these predictions involves the cosmic microwave background, that leftover glow from the Big Bang that Penzias and Wilson discovered. Inflation doesn't just explain why the CMB is so uniform. It also predicts specific patterns in the tiny temperature variations within the CMB, the 1 part in 100,000 deviations from perfect uniformity. Here's why. During inflation, the universe was governed by quantum mechanics at the smallest scales, and quantum mechanics, at its core, is about uncertainty. The Heisenberg uncertainty principle tells us that at very small scales, everything fluctuates. Energy fluctuates. Fields fluctuate. Even empty space fluctuates. These aren't vague, philosophical fluctuations. They're real, physical, measurable fluctuations that happen constantly at the quantum level. During inflation, these quantum fluctuations in the inflaton field were happening everywhere in the inflating space. Tiny, random variations in the field, here a little more energy, there a little less. Under normal circumstances, these fluctuations are incredibly tiny and average out to nothing on large scales. But inflation took these microscopic quantum fluctuations and stretched them to macroscopic, even cosmic, scales. Fluctuations that started smaller than an atom were expanded until they spanned millions of light years. Think about that. The largest structures in the universe, the great filaments of galaxies, the vast cosmic voids, the clusters and superclusters that span hundreds of millions of light years, all of them trace their origins back to quantum fluctuations. Tiny quantum jitters in a field that existed for less than a trillionth of a trillionth of a trillionth of a second, stretched by inflation until they became the seeds of everything. These stretched fluctuations became tiny variations in the density of the early universe. Slightly denser regions attracted more matter through gravity, and over billions of years, they collapsed to form galaxies, stars, planets. Slightly less dense regions became the great voids of the cosmic web. The entire large-scale structure of the universe, the whole grand architecture of reality, grew from quantum noise amplified by inflation. And here's where the prediction gets specific. Inflation predicts that these fluctuations should be nearly scale invariant. What that means is that the fluctuations should have roughly the same amplitude on all scales, whether you're looking at small patches of sky or large ones. Not exactly the same, there should be a slight tilt, with slightly more power on large scales, but nearly the same. This prediction is extremely precise and quite specific. A different mechanism for generating the early perturbations would give a different pattern. And when we look at the cosmic microwave background with satellites like COBE, WMAP, and Planck, that's exactly what we find. The fluctuations are nearly scale invariant, with exactly the slight tilt that inflation predicts. The match between prediction and observation is extraordinary. Let me tell you about those satellite missions, because they represent some of the most ambitious and precise scientific measurements ever made, and each one brought us closer to understanding what happened at the beginning of time. The first was COBE, the Cosmic Background Explorer, launched by NASA in 1989. COBE was designed to measure the cosmic microwave background with far greater precision than any previous instrument, and in 1992, the COBE team announced their results. They had detected, for the first time, the tiny temperature fluctuations in the CMB, variations of just a few millionths of a degree. The ripples in the afterglow of the Big Bang. The lead scientist on the Kobe project was George Smoot, and when the results were announced, the famous physicist Stephen Hawking called them the most important discovery of the century, if not of all time. That might sound like hyperbole, but think about what those ripples represent. They're the oldest light in the universe, carrying the imprint of quantum fluctuations from the first fraction of a second of cosmic history. They're the seeds from which everything, every galaxy, every star, every planet, every atom in your body, eventually grew. Smoot shared the Nobel Prize in 2006 for this discovery, along with John Mather, who led the Kobe team's measurement of the overall spectrum of the CMB. And that spectrum measurement deserves its own moment, because it was almost absurdly beautiful. Kobe measured the spectrum of the cosmic microwave background and found that it was a perfect blackbody spectrum. Now, a blackbody spectrum is the kind of radiation pattern you get from an object in thermal equilibrium, something that's at a uniform temperature and has been allowed to reach a steady state. The fact that the CMB has a perfect blackbody spectrum tells us that the early universe was, indeed, in thermal equilibrium, a hot, dense state where everything had settled to the same temperature. When Mather showed the spectrum at a scientific conference, the audience actually stood up and applauded. The data fit the theoretical blackbody curve so perfectly that you couldn't distinguish the data points from the theoretical prediction. It was one of those rare moments in science where the answer is unambiguous. But Kobe was just the beginning. Its resolution was limited, like looking at a landscape through frosted glass. You could see the broad outlines, but not the fine details. The next step was WMAP, the Wilkinson Microwave Anisotropy Probe, launched in 2001. WMAP mapped the entire sky with much higher resolution than Kobe, revealing the detailed structure of the CMB fluctuations. And the patterns it found were stunning. WMAP showed a specific pattern of hot and cold spots in the cosmic microwave background, and the statistical properties of those spots, their sizes, their distributions, their correlations, matched the predictions of inflation with remarkable precision. The data allowed cosmologists to nail down the age of the universe, 13.77 billion years, give or take about 40 million, the composition of the universe, about 5% ordinary matter, 27% dark matter, 68% dark energy, and the geometry of the universe, flat or very close to it. Every one of these measurements was consistent with what inflation predicts. And then came Planck. The European Space Agency's Planck satellite, launched in 2009, was the most precise CMB observatory ever built. Its resolution was extraordinary, its sensitivity unmatched. And when the Planck team released their final results, the match with inflationary predictions was tighter than ever. The spectral index, that measure of how the fluctuations vary with scale, was measured to be about 0.965, which is slightly less than 1.0. Inflation predicts a value slightly less than 1.0. The match is exquisite. Now, I should be honest here, because this is science, and honesty matters. While the evidence for inflation is very strong, and most cosmologists accept it as part of the standard cosmological model, it's not as rock-solid as, say, the evidence for the Big Bang itself. There are still debates, there are alternative ideas, and there's one prediction of inflation that has not yet been confirmed. A prediction that would, if detected, essentially seal the deal. That prediction involves gravitational waves. Gravitational waves are ripples in the fabric of space-time itself. Einstein predicted their existence in 1916 as a consequence of general relativity, but he thought they'd be too faint to ever detect. He was wrong about that, as it turns out. In 2015, the LIGO experiment, the Laser Interferometer Gravitational Wave Observatory, detected gravitational waves for the first time, produced by two black holes spiraling into each other about 1.3 billion light-years away. That detection was a triumph, and it won the 2017 Nobel Prize for Kip Thorne, Rainer Weiss, and Barry Barish. But the gravitational waves LIGO detected were produced by astrophysical events, collisions of massive objects. Inflation predicts a different kind of gravitational wave, primordial gravitational waves, produced by the exponential expansion itself. During inflation, quantum fluctuations in the fabric of spacetime were stretched by the expansion, just like the fluctuations in the inflaton field. These stretched fluctuations would have left a specific, subtle imprint on the cosmic microwave background, a particular pattern of polarization called B-mode polarization. Detecting this B-mode signal has been one of the holy grails of observational cosmology. In 2014, a team using the BICEP-2 telescope at the South Pole announced that they had detected it. The news was electric. It made headlines around the world. If confirmed, it would have been one of the greatest discoveries in the history of physics, direct evidence of inflation and of quantum gravity in one shot. But it wasn't confirmed. Further analysis, combined with data from the Planck satellite, showed that the BICEP-2 signal was likely caused by dust in our own galaxy, not by primordial gravitational waves. The detection was retracted. It was a painful moment for the team, but also a testament to the self-correcting nature of science. When you think you've found something extraordinary, you need extraordinary evidence, and the evidence wasn't there. The search continues. New experiments, like BICEP-3, the Simons Observatory, and the planned CMB-S4 project, are pushing to ever greater sensitivity. If primordial gravitational waves are there, these experiments may find them. And if they do, it will be one of the most profound discoveries in the history of science, a direct window into the first trillionth of a trillionth of a trillionth of a second of cosmic history. But let's come back to our central question for a moment, because I want to make sure the key idea has really landed. Why doesn't faster-than-light expansion violate Einstein's speed limit? Let me approach it from one more angle, because this idea is so important and so counterintuitive that it's worth circling back to. In special relativity, the speed of light is the maximum speed at which information can travel through space. If I'm here and you're over there, the fastest I can send you a message is at the speed of light. The fastest any particle, any signal, any influence can propagate from one point in space to another point in space is c. This is what prevents causality violations. This is what stops you from receiving a message before it was sent, which would create paradoxes. The speed of light isn't just a speed limit for stuff, it's the speed limit for causality itself. But expansion of space is different. When space expands, no information is being transmitted, no signal is being sent. Nothing is traveling from point A to point B. Points A and B are just getting farther apart because the space between them is growing. It's not communication, it's not motion, it's geometry changing. Here's another way to think about it. Imagine a coordinate grid, like graph paper, drawn on the floor. In special relativity, the speed of light says that nothing can move across the grid faster than a certain speed. But in general relativity, the grid itself can stretch. The lines can get farther apart. And when the grid stretches, objects that are sitting still on the grid, not moving at all relative to the grid, can end up farther apart. They're not moving through the grid. The grid is changing under them. This is what cosmologists mean when they talk about the metric expansion of space. The metric is the mathematical description of the distances between points. When the metric changes, distances change. even if nothing moves. And Einstein's speed limit applies to motion through the metric, not to changes in the metric itself. So the universe can expand faster than light because nothing is moving faster than light. Space is stretching. That's a completely different thing, and it's allowed, even expected, by the very same theory that gives us the speed limit. Now, this raises a really interesting question, one you might be thinking right now. If distant galaxies are receding from us faster than light because of the expansion of space, what happens to the light they emit? Can their light reach us? And the answer is, it depends. And this is where the concept of the observable universe comes in. The observable universe is not the same as the whole universe. The observable universe is the part of the universe from which light has had time to reach us since the Big Bang. It's like a sphere centered on us, with a radius of about 46.5 billion light-years. Wait, you might say, the universe is only 13.8 billion years old. How can the observable universe have a radius of 46.5 billion light-years? Wouldn't the maximum radius be 13.8 billion light-years, since light has only been traveling for that long? And this is a great question. The answer is that while the light has been traveling for 13.8 billion years, the space it's been traveling through has been expanding while the light is in transit. So the starting point of that light, the galaxy that emitted it, has moved much farther away during the time the light was en route. The light left when the galaxy was much closer, and by the time the light reaches us, the galaxy is much farther away. The 46.5 billion light-year radius of the observable universe reflects the current distance to those objects, accounting for the expansion that happened while the light was traveling. Beyond the observable universe, there's more universe. We just can't see it. Light from those regions hasn't had time to reach us yet. And for some of those regions, depending on the rate of expansion, light may never reach us. There are galaxies right now, in this very moment, that are receding from us so fast because of the expansion of space that the light they're emitting right now will never reach Earth. Not in a billion years. Not in a trillion years. Not ever. They're beyond our cosmic horizon, lost to us forever. This is one of those thoughts that can give you a sense of vertigo if you sit with it. The universe is much larger than what we can see, possibly infinitely larger. And there are regions of it that are forever inaccessible to us, not because there's a wall or a barrier, but because space is expanding between us and them faster than light can cross the gap. And yet, once upon a time, before inflation, all of these regions may have been in contact. They may have been neighbors. They may have been part of the same tiny, uniform, quantum-fluctuating patch of space. And then, inflation blew them apart, scattering them across distances so vast that they'll never see each other again. There's something poetic about that, don't you think? Everything we can see, and everything we can't, may have once been part of the same infinitesimal speck, connected, unified, and now separated by the unstoppable stretching of space itself. Let me tell you about something else that inflation does, something that connects the very small to the very large, in a way that's almost magical. Remember those quantum fluctuations I mentioned earlier? The tiny, random variations in the inflaton field during inflation? Well, those fluctuations didn't just create the seeds of galaxies. They also created something called the cosmic web. If you could zoom out far enough, farther than any telescope can see, far enough to see the large-scale structure of the universe, you'd see something remarkable. Galaxies aren't scattered randomly through space. They're arranged in a vast, three-dimensional web. Filaments of galaxies, long, thin strands stretching across hundreds of millions of light-years, connect at nodes where great clusters of galaxies gather. Between the filaments are enormous voids, vast empty regions of space with almost no galaxies at all. The whole thing looks strikingly like a neural network, or like the veins in a leaf, or like a close-up of foam. This cosmic web, this grand architecture of the universe, grew directly from the quantum fluctuations of inflation. The slightly denser regions, where the inflaton field had a tiny bit more energy, attracted more matter through gravity over billions of years. They pulled in gas, formed stars, built galaxies. The slightly less dense regions emptied out, becoming the voids. The pattern you see in the large-scale structure of the universe is, in a very real sense, a blown-up photograph of quantum mechanics. The universe is a giant amplifier. It took the smallest possible fluctuations in reality and turned them into the largest structures that exist. Every galaxy you'll ever see through a telescope, including the Milky Way, including the solar system, including you, traces its existence back to a quantum fluctuation during inflation, a random jitter in a field that existed for a sliver of a moment, in a universe younger than the tiniest fraction of the blink of an eye, became the reason you're here tonight, breathing, thinking, existing. And that's not poetry, that's physics. Let's talk about something that might seem like a detour, but I promise it's not. Let's talk about what space actually is. Because when we say space is expanding, that's a statement that only makes sense if you have some picture in your head of what space is. And most of us, if we're honest, think of space as nothing, empty, the void, the stage on which things happen, but not a thing itself. But physics tells us something different. Space, or more precisely space-time, is a physical thing. It has properties. It can bend, stretch, ripple, and expand. It has a structure. It's not just the absence of stuff. It's a something in its own right. And understanding this is crucial to understanding why its expansion doesn't violate the speed of light. Let's go back to Einstein for a moment, because this is really his idea. Before Einstein, people thought of space the way Newton did, as an absolute, fixed, unchanging container. Space was the stage. Time was the clock. They existed independently of the actors on the stage. Nothing that happened in the universe could affect space or time themselves. They were just there, immutable and eternal. Einstein demolished this picture. In special relativity, he showed that space and time are interwoven into a single four-dimensional fabric, space-time, and that the way you experience space and time depends on how you're moving. If you're moving fast relative to me, your clocks tick slower than mine, your lengths contract, and we disagree about which events happen simultaneously. Space and time aren't absolute. They're relative to the observer. And then, in general relativity, he went further. He showed that this space-time fabric isn't just a passive background. It's dynamic. It responds to the matter and energy within it. Mass and energy curve space-time, and the curvature of space-time tells matter how to move. As the physicist John Wheeler later summarized it, space-time tells matter how to move. Matter tells space-time how to curve. It's a conversation, a feedback loop. Space isn't a stage, it's a participant. This is why space can expand, because space is a physical thing with dynamical properties. It's governed by equations, Einstein's field equations, and those equations say that the geometry of space changes over time in response to the distribution of energy within it. Under the conditions that existed in the very early universe, those equations say space should expand exponentially. That's not a violation of physics. It's physics operating exactly as the equations describe. Now, I want to come back to something I mentioned earlier, because it's one of the most mind-bending aspects of inflation, and it deserves more attention. I mentioned that during inflation, quantum fluctuations were stretched to cosmic scales. Let me unpack what that means a bit more, because it touches on one of the deepest connections in all of physics, the relationship between quantum mechanics and gravity, between the very small and the very large. Quantum mechanics is the physics of the very small. It governs atoms, electrons, photons, quarks. At the quantum level, everything is fuzzy. Particles don't have definite positions until you measure them. Fields fluctuate randomly, popping in and out of existence. Energy can be borrowed from the vacuum for brief moments. The quantum world is a world of probability, uncertainty, and weirdness. Gravity, as described by general relativity, is the physics of the very large. It governs planets, stars, galaxies, the universe itself. At the gravitational level, everything is smooth. Space-time curves in response to mass and energy. Objects follow geodesics, the straightest possible paths through curved space. The gravitational world is a world of geometry, curvature, and elegance. These two theories, quantum mechanics and general relativity, are the two pillars of modern physics. And here's the awkward truth. They don't get along. They're both incredibly successful in their own domains. But when you try to combine them, when you try to apply quantum mechanics to gravity, or general relativity to the quantum scale, the math breaks down. You get infinities, contradictions, nonsense. Finding a way to unify them, to create a theory of quantum gravity, is arguably the single biggest unsolved problem in all of physics. But inflation is one of the few contexts where the two theories touch. During inflation, quantum fluctuations, quantum mechanics, were imprinted onto the large-scale structure of space-time, general relativity. The very small shaped the very large. The probabilistic jitters of quantum fields became the deterministic architecture of the cosmos. This is extraordinary. It means that when we look at the cosmic microwave background, when we map the distribution of galaxies, we're seeing the fingerprints of quantum mechanics written across the sky. This is why the search for primordial gravitational waves is so important. If quantum fluctuations during inflation also produced gravitational waves, ripples in space-time itself, then detecting those waves would be direct evidence of quantum effects on space-time. It would be a glimpse of quantum gravity, the holy grail of theoretical physics. Not a full theory, but a data point, a foothold, a clue. And that's why the Bicep 2 false alarm was so painful. For a brief, exhilarating moment, physicists thought they'd found it. The first direct evidence of quantum gravity. The first time the quantum and gravitational worlds had been caught interacting. And then the dust got in the way. Literally, galactic dust. But the search goes on. And someday, maybe soon, we'll get there. Let me take you on another tangent, because it's one of my favorite parts of this story. Let's talk about what inflation implies about the size of the universe. I mentioned that the observable universe has a radius of about 46.5 billion light-years. That's already enormous. The number of galaxies in the observable universe is estimated at around 2 trillion. Each of those galaxies contains billions of stars. The scale is already beyond comprehension. But the observable universe may be a tiny, almost infinitesimal fraction of the whole thing. Here's why. Inflation expanded the universe by a factor of at least 10 to the 26. But the observable universe, the part we can see, has a radius that corresponds to a much smaller expansion. The region that became our observable universe was a tiny patch within the much larger inflated space. And everything beyond the edge of the observable universe, everything beyond the light horizon, is more universe. Same laws of physics, same kinds of galaxies and stars, just beyond our ability to see. How much more? We don't know for certain, but the numbers that come out of most inflationary models are staggering. Some estimates suggest that the total universe could be 10 to the 23 times larger than the observable universe in radius. Others suggest even more. Some models predict a universe so large that writing the number of times bigger than the observable universe in standard notation would require more digits than there are atoms in the observable universe. Just sit with that for a moment. The observable universe, with its 2 trillion galaxies and its hundreds of billions of trillions of stars, might be an unimaginably small speck within the full extent of what inflation created. We'd be like bacteria living on a single grain of sand, unaware of the entire Sahara Desert stretching out in every direction. And here's where it gets even stranger. Because some versions of inflationary theory predict not just a very large universe, but an infinite one. Or more precisely, they predict that once inflation starts, it never really stops everywhere. It stops in some regions, like our observable universe, but continues in others. And in the regions where it continues, new Big Bangs happen. New regions of normal space emerge, each one potentially with different physical properties, different constants of nature, different laws of physics. This idea is called eternal inflation, and it was developed extensively by André Linde in the 1980s, building on work by Alexander Vilenkin. In the eternal inflation picture, our universe is just one bubble in an infinite, ever-expanding foam of universes. Each bubble is a separate pocket universe, born from a local ending of inflation, expanding and cooling and forming galaxies and stars, and the foam keeps inflating, producing new bubbles endlessly. Its universes all the way down. This is the multiverse, and it's one of the most controversial ideas in modern physics. Now, I want to be careful here, because this is a topic where it's easy to slip from established science into speculation, and it's important to be clear about where the boundary lies. The basic idea of inflation, a brief period of exponential expansion in the very early universe, is well supported by evidence. The predictions it makes about the cosmic microwave background, the flatness of space, the large-scale structure of the universe, all of these are confirmed by observations. Most cosmologists accept inflation as part of the standard model of cosmology. Eternal inflation and the multiverse are extensions of the basic inflationary idea. They follow naturally from the mathematics of many inflationary models. If you take the equations seriously, eternal inflation is hard to avoid. But, and this is a big but, these extensions are not directly testable. We can't observe other bubble universes. We can't send probes beyond our cosmic horizon. We can't verify that the multiverse exists. This raises deep questions about the nature of science. Is an idea scientific if it follows logically from a well-supported theory but can't be directly tested? Some physicists say yes, that the multiverse is a legitimate prediction of inflation and should be taken seriously. Others say no, that a prediction that can never be falsified isn't really a scientific prediction at all. This debate has been going on for decades, and it's not settled. What I find beautiful about this debate is that it shows how inflation pushes us to the very edge of what science can address. It starts with a concrete, testable prediction, the smoothness of the cosmic microwave background, and leads, step by logical step, to questions about the nature of reality that border on philosophy. How many universes are there? Are the laws of physics unique, or just local? Is our universe special or typical? These aren't questions physics was designed to answer. And yet, here we are. But let's pull back from the edge and return to firmer ground. Let's talk about something we can observe, something that connects inflation to the universe you see when you look up at the night sky. Let's talk about how galaxies formed. In the very early universe, right after inflation ended and the normal hot Big Bang took over, the universe was a nearly uniform sea of hot plasma. Protons, electrons, photons, all mixed together in a blinding, opaque fog. There were no stars, no galaxies, no structure of any kind, just a smooth, hot soup. But embedded in that soup were the tiny density fluctuations left behind by inflation, regions that were very slightly denser than average, and regions that were very slightly less dense. These fluctuations were incredibly small, just 1 part in 100,000, but they were enough. Over time, gravity amplified them. The slightly denser regions pulled in a little extra matter. That extra matter made them denser still, which pulled in even more matter. It's a positive feedback loop, gravity's favorite trick. Over hundreds of millions of years, the denser regions grew and grew until they became dense enough to collapse, forming the first stars, the first galaxies, the first clusters. This process, gravitational instability, is the engine that built every structure in the universe, and it all started with those quantum fluctuations from inflation. Without them, the universe would have remained perfectly smooth, a uniform sea of gas with no structure at all. No galaxies, no stars, no planets. No you. Quantum mechanics, amplified by inflation, is the reason any of this exists. The first stars, by the way, are thought to have formed about 100 to 200 million years after the Big Bang. They were monsters, far more massive than our sun, hundreds of times more massive, maybe even 1,000 times. They burned hot and bright and died young, living only a few million years before exploding as supernovae or collapsing into black holes. These first-generation stars are called population 3 stars, and we've never directly observed one. They're too far away and too far back in time. But theoretical models predict their properties, and the next generation of telescopes, like the James Webb Space Telescope, may eventually detect their light. When those first stars died, they scattered heavy elements into the surrounding gas, elements forged in their cores and in their explosive deaths. Carbon, oxygen, nitrogen, iron, the elements that would eventually form planets and organic molecules and living things. The first stars seeded the universe with the raw materials for everything that came after, and then the next generation of stars formed, enriched with those heavier elements, and they formed planets. And on at least one of those planets, around at least one of those second or third generation stars, chemistry became biology. Molecules became cells. Cells became organisms. And eventually, after 4.5 billion years on this particular planet, organisms became curious enough to look up at the stars and ask where it all came from. The chain of causation runs all the way from quantum fluctuations during inflation to you, lying here right now, listening to this story. And every link in that chain is physics. Every step is governed by equations we can write down. The universe is, in some deep sense, comprehensible. Not fully comprehended, not yet, but comprehensible. Open to understanding, willing to be known. That's a pretty amazing thing to fall asleep thinking about. Now let's talk about something that makes the whole story even more interesting: dark energy. Because it turns out, the faster-than-light expansion of the universe isn't just something that happened in the past, during inflation. In a gentler but equally profound way, it's happening right now. And the reason is one of the biggest mysteries in all of physics. In 1998, two teams of astronomers made a discovery that stunned the scientific community. They were studying a particular type of exploding star called a Type Ia supernova. These supernovae are special because they all explode with roughly the same intrinsic brightness, which makes them useful as standard candles. By comparing how bright a Type Ia supernova appears to us versus how bright it actually is, astronomers can figure out how far away it is. And by measuring the redshift of the host galaxy, they can figure out how fast it's receding. The two teams, the Supernova Cosmology Project led by Saul Perlmutter, and the High-Z Supernova Search Team led by Brian Schmidt and Adam Rees, were both trying to measure how fast the expansion of the universe is slowing down. Because the expectation was that it was slowing down. Gravity pulls matter together, and the mutual gravitational attraction of all the matter in the universe should be gradually decelerating the expansion, like a ball thrown upward, gradually slowing as gravity pulls it back. But that's not what they found. Both teams, working independently, found that the expansion of the universe isn't slowing down at all. It's speeding up. The expansion is accelerating. Distant supernovae were farther away than they should have been if the expansion were decelerating. Something was pushing the universe apart, making it expand faster and faster over time. This was completely unexpected. It was like throwing a ball into the air and watching it accelerate upward, moving faster and faster away from you, as if something invisible were pushing it. Gravity should be slowing the expansion down. Instead, something else, something stronger than gravity, something unknown, is speeding it up. That something has been given a name, dark energy. And despite the name, it's not energy in the usual sense. It's whatever is causing the accelerating expansion. We call it dark because we can't see it, can't detect it directly, and frankly, we don't really know what it is. It's one of the deepest mysteries in all of modern science. Here's what we do know. Dark energy makes up about 68% of the total energy content of the universe. That's more than everything else combined. Ordinary matter, the stuff you and I and stars and planets are made of, is only about 5%. Dark matter, the invisible stuff that provides the extra gravity needed to hold galaxies together, is about 27%. And dark energy is the remaining 68%. The universe is dominated by something we don't understand. The simplest explanation for dark energy is that it's a property of space itself. That empty space has energy. That every cubic meter of vacuum, of nothing, contains a small but non-zero amount of energy, and that this energy exerts a negative pressure, a repulsive gravitational effect that pushes space apart. Sound familiar? It should. Because this is almost exactly the same mechanism that drove inflation. During inflation, the inflaton field was in a high-energy state with negative pressure, and the repulsive gravitational effect of that negative pressure drove exponential expansion. Dark energy does the same thing, just much, much more gently. And here's the thing that brings the story full circle. The cosmological constant that Einstein added to his equations in 1917, the fudge factor he later called his biggest blunder, is mathematically equivalent to a constant energy density of the vacuum. Einstein invented a term for energy in empty space, abandoned it, and then it turned out to be real. The universe has a cosmological constant. It's just not the one Einstein intended. His was designed to hold the universe still. The real one is making it accelerate. So right now, tonight, the expansion of the universe is accelerating. And this means that the universe's expansion is, in some sense, inflating again, just much more slowly than it did in the first fraction of a second. The same physics that drove the universe's fastest-than-light expansion at the beginning is driving a gentler but relentless acceleration right now. Galaxies that are already far from us are being pushed farther away, faster and faster, and this has profound implications for the future of the universe. Let me paint a picture for you of where this is heading, because it's equal parts beautiful and melancholy. As the expansion accelerates, distant galaxies will recede from us faster and faster. Eventually, they'll cross our cosmic horizon, the boundary beyond which light can never reach us. One by one, the galaxies we can currently see will disappear over that horizon, like ships sailing over the edge of the sea, slipping below the curve of the cosmos. Their light will redshift toward infinity, stretching to longer and longer wavelengths until it becomes undetectable. In the very far future, trillions of years from now, an observer in our galaxy, or whatever our galaxy has become by then, would look out and see nothing, no other galaxies, no cosmic microwave background, no evidence that a Big Bang ever happened. The observable universe would contain just the local gravitationally bound group of galaxies, everything else having been swept away by the expansion. The sky would be empty. The evidence for the origin and history of the universe would be erased. There's a wonderful paper by the physicists Lawrence Krauss and Robert Scherer, written in 2007, that spells this out in detail. They point out that future astronomers living in this empty sky era would have no way of knowing that the universe was once full of galaxies. They would have no way of discovering the expansion of the universe, because there would be nothing left to see receding. They would be living in a universe that, to them, would look static and eternal. Exactly the kind of universe that Einstein assumed when he added his cosmological constant. There's a deep irony in that. The very mechanism that's currently helping us understand the universe, the expansion of space, will eventually erase all the evidence that it ever existed. Future civilizations might never know what we know tonight. We're living in a cosmologically privileged time, a window when the universe still reveals its secrets to anyone patient enough to look. Makes you want to appreciate it while we can, doesn't it? Now, let me bring us back to the physics one more time, because there's a subtlety about dark energy that's worth dwelling on. Remember, I said that the expansion of the universe can make distant galaxies recede from us faster than light? That's happening right now, because of dark energy. Galaxies beyond a certain distance, called the Hubble radius, currently about 14.4 billion light-years, are receding from us at speeds greater than the speed of light. And galaxies well beyond that distance are receding much faster still. And just like during inflation, this doesn't violate Einstein's speed limit. The galaxies aren't moving through space faster than light. Space is expanding between us and them, faster than light can cross the gap. The rule stands. The universe obeys its own laws, even when it does things that sound impossible. But here's something that might surprise you. Even though a galaxy might be receding from us faster than light right now, light that it emitted in the past can still reach us. The light from a galaxy that's currently receding faster than light was emitted when the galaxy was closer, when the recession speed was slower, and the light has been fighting its way toward us through the expanding space ever since. In some cases, the light initially moves backward, relative to us, because the expansion is carrying it away. But as it enters regions of space where the expansion rate is slower, because those regions are closer to us, it gains ground and eventually reaches us. It's like swimming against a current in a river. Near the source, the current is strong, and you're swept backward. But as you get farther from the source, the current weakens, and you can make progress. The light from very distant galaxies has been swimming against the current of expansion for billions of years, and some of it has made it to our shores. That's why the observable universe has a radius of 46.5 billion light-years, even though the universe is only 13.8 billion years old. We're seeing light from objects that were once much closer, but are now impossibly far away. This interplay between expansion and the propagation of light is one of the most beautiful and subtle aspects of modern cosmology. It's a dance, really. Light moves through space at the speed of light, always. But space is moving under it, stretching the distance it needs to cover, shifting its wavelength, altering its journey. Whether the light eventually reaches us or is forever lost beyond the horizon depends on the detailed history of the universe's expansion. It's a cosmic race between light and space, and the outcome isn't always the same. Let me take a moment to talk about one more aspect of inflation that I find deeply fascinating, something that brings together ideas from particle physics, thermodynamics, and cosmology in a way that few other topics do. Let's talk about what happened when inflation ended, the moment called reheating. During inflation, the universe was cold. That might seem counterintuitive, since we often describe the Big Bang as starting with extreme heat, but inflation actually cooled the universe down. Think about it. When you expand a gas rapidly, it cools. That's how your refrigerator works. The exponential expansion of inflation diluted everything that existed before it and cooled the universe to near absolute zero. But then inflation ended. The inflaton field rolled down to its ground state and released all its stored energy. That energy flooded into the universe as a blast of particles and radiation, reheating the cosmos to fantastically high temperatures, perhaps as high as 10 to the 27 Kelvin or more. This is the moment when the universe became the hot, dense, particle-filled place that we think of as the Big Bang. So in a sense, inflation preceded the hot Big Bang. The hot Big Bang didn't start from a singularity in the way the original theory described. Instead, it started from the end of inflation. The reheating at the end of inflation created the initial conditions for the hot, dense, expanding universe that eventually cooled, formed atoms, released the cosmic microwave background, and evolved into the cosmos we see today. This means that the Big Bang, as most people picture it, this primordial explosion from a single point, isn't quite right. There was no explosion. There was a rapid expansion of space, driven by the inflaton field, followed by a conversion of the field's energy into particles and heat. The violence happened, but it was the violence of space expanding, not of stuff exploding outward from a center, and it happened everywhere at once, not at a particular point. I know that's a lot of ideas to hold in your head at once. So let me give you a simple version of the timeline, just to anchor everything we've talked about. First, there's the very beginning, about which we know almost nothing. We might need a theory of quantum gravity to describe it. This is the Planck era, before about 10 to the minus 43 seconds. Then, at around 10 to the minus 36 seconds, inflation begins. The inflaton field is in a high-energy state with negative pressure. Space expands exponentially, doubling in size dozens of times. Quantum fluctuations are stretched to cosmic scales. Trust your dreams for the future. At around 10 to the minus 32 seconds, inflation ends. The inflaton field decays, dumping its energy into particles and radiation. The universe is reheated to extreme temperatures. The hot Big Bang begins. Over the next few minutes, the universe cools enough for nuclear fusion to happen. Protons and neutrons combine to form the nuclei of hydrogen, helium, and a little lithium. This is Big Bang nucleosynthesis, and the predicted abundances of these elements match what we observe beautifully. At about 380,000 years, the universe cools enough for electrons to combine with nuclei to form neutral atoms. Light is freed from the plasma and travels across the universe. This light is the cosmic microwave background. Over the next few 100 million years, gravity slowly amplifies the density fluctuations from inflation, eventually forming the first stars and galaxies. And then billions of years of cosmic evolution, stars forming and dying, galaxies merging, heavy elements being forged, planets forming, and eventually, life emerging. That's the story, from quantum fluctuations to you, from the inflaton field to the sound of these words, from a universe smaller than a proton to 193 billion light-years across and growing. And there's something I want to come back to now, something we've been circling around for a while. It's the question of what drove inflation. What is this inflaton field? What kind of thing is it? And what does it tell us about the nature of reality? The honest answer is, we don't know what the inflaton field is. Not really. We know what properties it needs to have. It needs to be a scalar field, a field that has a value at every point in space but no direction, unlike electric or magnetic fields, which point in a particular direction. It needs a potential energy function that allows it to linger in a high-energy state long enough for inflation to happen, and then roll down to a lower state, dumping its energy into reheating. Beyond that, the identity of the inflaton is one of the big open questions in cosmology and particle physics. Is the inflaton a new, fundamental field that exists only at extremely high energies, one we've never directly detected? Is it related to the Higgs field, the field that gives particles their mass? The Higgs boson was discovered at the Large Hadron Collider in 2012, confirming the existence of the Higgs field. And there are models of inflation that use the Higgs field, or something closely related to it, as the inflaton. But these models face challenges, and the connection is far from established. Could the inflaton be something even more exotic? In string theory, there are many possible scalar fields associated with the shapes and sizes of extra dimensions. Some string theorists have proposed that one of these fields could be the inflaton, but string theory itself hasn't been tested, and these proposals are highly speculative. The truth is, the inflaton field is one of the most important things in the history of the universe, and we don't know what it is. We know it existed, or at least, something that behaves exactly like it existed, because the predictions match the observations. But its fundamental nature remains a mystery. It's a bit like knowing that a crime was committed, having all the forensic evidence, but not being able to identify the perpetrator. This is one of the things I love about physics. It's not a completed picture. It's a work in progress. We know so much, an astonishing amount, really, about the first fraction of a second of cosmic history. And yet, there are gaps. Deep, humbling gaps. Places where the map says, "Here be dragons," and we have to admit we don't know what's there. The inflaton field is one of those dragons. Dark energy is another. The nature of dark matter. The unification of quantum mechanics and gravity. The initial singularity, or whatever really happened at the very beginning, before inflation. These are the frontiers, the edges of knowledge, the places where the next generation of discoveries will be made. And there's something wonderful about lying here in the dark, knowing that these mysteries exist, that the universe hasn't given up all its secrets yet, that the story isn't over, that somewhere, right now, a physicist is staring at an equation on a whiteboard, or running a simulation on a supercomputer, or analyzing data from a telescope, trying to push the boundary just a little bit further. And maybe they'll have their own spectacular realization moment, like Guth did on that December evening in 1979. Let me tell you one more story about inflation, one that I think captures the human side of this science beautifully. In March 2014, when the BICEP-2 team announced their, ultimately incorrect, detection of primordial gravitational waves, a video was made of Andre Linde learning the news for the first time. A colleague, Chao Lin Kuo, who was part of the BICEP-2 team, went to Linde's door at Stanford to tell him in person. In the video, Kuo knocks on the door. Linde opens it, and Kuo says something like, "I have a surprise for you." He tells Linde that they've detected B-mode polarization in the CMB, with a signal strength that matches inflationary predictions. Linde's face changes. He's stunned. He puts his hand to his mouth. His wife, Renata Kalash, who is also a physicist, comes to the door. Linde says, "What?" He looks like he might cry. He says something about how he's always lived with the fear that the theory might be wrong, that inflation might not be real, and now, if this is true. It turned out not to be true, of course. The signal was from dust, not from inflation. But that moment, Linde's face, his vulnerability, his decades of wondering whether the idea he'd spent his career developing was right, that's the human side of physics. These aren't abstract questions for the people who work on them. They're personal, they're emotional, they're the work of a lifetime, and the fact that the BICEP-2 result didn't hold up doesn't diminish inflation. The theory still stands on its other predictions, which have been confirmed. The primordial gravitational waves may simply be too faint for current instruments to detect, or they may be at a level that's just barely below the current sensitivity limits. Future experiments will push deeper, and someday, perhaps, someone will knock on another physicist's door with news that this time holds up. Let me shift gears now and talk about something that connects inflation to a broader philosophical question that I think is worth sitting with as you drift toward sleep. It's the question of why the universe is the way it is. I don't mean why in a theological sense or in a purpose-driven sense. I mean why in a physical sense. Why does the universe have the properties it has? Why these laws and not others? Why these values of the fundamental constants and not different ones? Inflation, especially in its eternal inflation version, offers a possible answer to this question, and it's an answer that some people find satisfying and others find deeply unsettling. If eternal inflation is correct, then our universe is just one of an enormous, possibly infinite number of pocket universes, each with potentially different properties. The constants of nature, things like the strength of gravity, the mass of the electron, the speed of light, might not be fundamental constants at all. They might be local properties, different in different pocket universes, determined by the specific way inflation ended in each region. In that case, asking, why is the speed of light 299,792,458 meters per second, is a bit like asking, why is the temperature outside 72 degrees? The answer is, because you happen to be in a place where it's 72 degrees. In other places, it's different. There's no deep reason for this particular value. It's just where you are. This idea is called the anthropic principle in its strong form. We observe the values of the constants that we do, because only those values are compatible with the existence of observers like us. In a universe where the constants were different, there might be no galaxies, no stars, no chemistry, no life. We couldn't be there to observe it. We can only exist in a universe that permits our existence. So of course, we find ourselves in one that does. Some physicists find this deeply unsatisfying. It feels like giving up on explanation. Instead of finding a fundamental reason for why the constants have the values they do, we're saying, there's no reason, it's just random. and we exist in a corner of the multiverse where the randomness happened to allow us. Others find it perfectly reasonable. After all, we don't demand a fundamental reason for why Earth is 93 million miles from the Sun. It just is. If it were much closer, or much farther, we wouldn't be here to ask the question. The anthropic approach to the fundamental constants is the same logic applied at a much larger scale. And here's the thing. This debate isn't settled. It may not be settleable. It depends on questions about the nature of the multiverse that we may never be able to answer observationally. It's one of those places where physics shades into philosophy, where the questions we can formulate outstrip our ability to test them. But I think there's value in holding these questions open, in not rushing to answers, in being comfortable with not knowing. The universe has been around for 13.8 billion years, and we've been doing science for maybe 400. We've figured out an astonishing amount in that time. But the idea that we should have all the answers by now, or even most of them, is a kind of cosmic hubris. The universe is vast and strange and deep, and we're just getting started. Let me bring us to another thread that ties into our story, the relationship between inflation and the arrow of time. You might not think about it much, but there's something deeply puzzling about the fact that time has a direction. Things happen in a particular order. Eggs break but don't unbreak. Coffee cools down but doesn't spontaneously heat up. You remember the past but not the future. This directionality of time is so obvious, so woven into our daily experience, that it seems like it shouldn't need explaining, but it does. The fundamental laws of physics are almost all time symmetric. If you watched a movie of two particles bouncing off each other and then ran the movie backwards, both versions would obey the laws of physics equally well. There's nothing in the equations of motion that picks out a direction of time. And yet, time clearly has a direction. Entropy increases, disorder grows, things run down. The resolution, as far as we understand it, has to do with initial conditions. The universe started in a state of incredibly low entropy, incredibly high order. And the natural tendency of any system that starts in a low entropy state is to evolve toward higher entropy, more disorder. That's the second law of thermodynamics, and it's what gives time its arrow. But why did the universe start in such a low entropy state? That's one of the deepest questions in all of physics, and inflation may provide part of the answer. During inflation, the universe was in a very simple, very smooth, very uniform state. The exponential expansion ironed out all the wrinkles, diluted all the particles, smoothed out all the inhomogeneities. It left the universe in an incredibly ordered, low-entropy condition. And then, when inflation ended and the universe reheated, all that stored energy was released, and the universe began its long climb toward higher entropy, more structure, more complexity, more disorder. So in some sense, inflation set the initial conditions that gave rise to the arrow of time. It created the ordered starting point from which the universe has been evolving ever since. Without inflation, or without something like it, it's hard to explain why the early universe was so smooth, so ordered, so primed for the emergence of structure and complexity and eventually life. Now, this is a somewhat speculative idea. Not everyone agrees that inflation fully explains the low entropy of the early universe. Roger Penrose, for example, one of the greatest mathematical physicists alive, has argued that inflation doesn't actually solve the entropy problem, it just pushes it back a step. Why was the inflaton field in such a special, low-entropy state to begin with? Why was it sitting at the top of its potential energy hill? That requires its own explanation, and inflation doesn't provide one. Penrose has proposed his own alternative to inflation, called conformal cyclic cosmology, in which the universe goes through an infinite series of cycles, with each Big Bang being the continuation of the previous universe's far future. It's a fascinating idea, though the evidence for it is still debated. The point is that the question of initial conditions, of why the universe started the way it did, is one of the deepest and most unresolved questions in physics. Inflation provides a partial answer, and a very good one, but it doesn't close the book. There are still chapters to be written. Let me tell you something about the Hubble constant, because it ties into our story in a way that's both fascinating and a little bit maddening. And it also shows you how science works at the frontier, where things are messy and uncertain and genuinely unresolved. The Hubble constant, usually written as h0, tells you how fast the universe is expanding right now. Specifically, it says that for every megaparsec of distance, a megaparsec is about 3.26 million light-years, galaxies are receding from each other at a certain speed. Measure h0 and you know the expansion rate. Simple, right? Except it isn't. Because for the last several years, two different methods of measuring the Hubble constant have been giving two different answers. And the disagreement is statistically significant. It's not a matter of fuzzy measurement error. The numbers genuinely disagree, and nobody knows why. One method uses the cosmic microwave background. The Planck satellite mapped the CMB with extraordinary precision, and from its data, cosmologists can infer the expansion rate of the early universe, and then use the standard cosmological model, which includes inflation, dark matter, and dark energy, to extrapolate what the Hubble constant should be today. This gives a value of about 67.4 kilometers per second per megaparsec. The other method uses the cosmic distance ladder. It measures the distances to nearby galaxies using Cepheid variable stars, stars whose brightness varies in a predictable way, allowing astronomers to calculate their distance, and type 1a supernovae, and then directly measures the recession speeds of those galaxies. This gives a value of about 73 kilometers per second per megaparsec. The difference, about 6 kilometers per second per megaparsec, might not sound like much, but given the precision of the measurements, it's huge. The two values are inconsistent at the level of about 4 to 5 standard deviations, which in statistical terms means the probability of this being a random fluke is less than 1 in 100,000. This discrepancy is called the Hubble tension, and it's one of the most hotly debated topics in cosmology today. There are basically three possibilities. First, one of the measurements could be wrong. There might be a systematic error in either the CMB analysis or the distance ladder measurements that nobody has found yet. Teams on both sides have checked and rechecked their work, but systematic errors can be subtle. This is the most conservative explanation. Second, the standard cosmological model might be wrong, or at least incomplete. The model used to extrapolate from the early universe to today assumes certain things about dark energy, about the number of neutrino species, about the history of the expansion. If any of those assumptions are wrong, the extrapolation would give the wrong answer. Maybe dark energy isn't constant, but varies over time. Maybe there's a new type of particle or force that we haven't accounted for. This would be exciting, because it would mean new physics. Third, and this is the most tantalizing possibility, maybe the Hubble tension is telling us something about inflation. Some physicists have proposed models of early dark energy, a brief burst of extra energy in the early universe, shortly after inflation, that would speed up the expansion rate and bring the two measurements into agreement. This would be a modification of the standard cosmological model, but a relatively gentle one, and it would add another layer to the story of the universe's expansion. As of right now, the Hubble tension is unresolved. It might be a measurement error. It might be new physics. We don't know. And I find that thrilling, not frustrating. Because it means the story isn't over. There's still something out there, something the universe is doing that we don't fully understand, and someone is going to figure it out. Maybe it'll be a graduate student staring at data at 3 in the morning, having their own spectacular realization. That's how it works. The universe drops clues, and we pick them up, one by one. Let me bring us into another territory now, something that's a bit more speculative, but deeply connected to everything we've been discussing. Let's talk about the very beginning, not just the beginning of inflation, but the beginning of the beginning. What, if anything, came before inflation? What started it all? This is one of the hardest questions in all of physics, and I want to be upfront. We don't have a good answer. We have ideas, some of them beautiful and some of them crazy, and some of them both, but we don't have a confirmed theory. Here's the problem. Inflation explains the hot Big Bang. It tells us how the universe got to be the way it was at the start of the hot, dense phase. But what started inflation? What put the inflaton field in its high-energy state? What existed before inflation began? In some models, inflation is eternal to the past as well as to the future. That is, there was no beginning. Inflation has always been happening somewhere, with pocket universes bubbling off endlessly. In this picture, asking, what came before inflation, is like asking, what's north of the North Pole? The question doesn't apply. There is no before. But many physicists find this unsatisfying. Eternal inflation has its own puzzles and paradoxes, including deep questions about probability and measure theory that haven't been resolved. And the idea that the universe has no beginning feels, to some, like it's sweeping the question under the rug rather than answering it. Other models propose that the universe emerged from a quantum fluctuation. Alexander Vilenkin, a physicist at Tufts University, proposed in the 1980s that the universe could have tunneled into existence from literally nothing, not from empty space, because empty space is still something, from nothing. No space, no time, no matter, no energy, just the equations of quantum mechanics, which allow a wave function to describe the probability of a universe popping into existence. And if the probability is non-zero, then eventually, or perhaps eventually, doesn't even apply. Since there was no time, it happens. This is an extraordinary idea, a universe from nothing. But what does nothing mean in this context? Is it really nothing? Or is it quantum mechanics, which is something? And where do the laws of quantum mechanics come from? You can see how the questioning can spiral into an infinite regress. Stephen Hawking and James Hartle proposed a related idea in 1983, called the no-boundary proposal. In their model, the universe has no boundary in time. If you go back toward the beginning, time doesn't end at a singularity. Instead, it smoothly rounds off, like the surface of a sphere. Just as the surface of the Earth has no edge, you can keep walking south and eventually you start going north. The space-time of the universe has no beginning. Time just fades into space. The distinction between time and space becomes blurred as you approach the very beginning, and the question, what came before, loses its meaning because there is no before. The universe is finite but unbounded, complete in itself. This is one of those ideas that's beautiful in its mathematical elegance, but profoundly difficult to wrap your head around. Time becoming space. The beginning that isn't a beginning. A universe that simply is, without a first moment. And there are other proposals too. Some involve collisions between higher dimensional membranes in string theory, so-called brane cosmology. Some involve a cyclic universe that bounces through alternating phases of expansion and contraction. Some involve quantum gravity effects, that smooth out the initial singularity and replace it with a big bounce. None of these has been confirmed. None of them may be confirmable with current technology. But here's what I find comforting about all of this uncertainty. We're asking the right questions. We may not have the answers yet, but the questions themselves are well posed, mathematically precise, and in principle testable, if we can build the right instruments or find the right observations. And that's progress. That's the scientific method working as it should. You don't need to have the answer to be doing good science. You just need to be asking questions that nature might eventually answer. Let me bring us back to something tangible for a moment. Let me talk about the speed of light one more time, because I want to make sure we've fully appreciated how strange and beautiful it is. The speed of light isn't just the speed that photons happen to travel at. It's built into the structure of space-time. It's the maximum speed at which causality can propagate. It defines the relationship between space and time. In some very real sense, the speed of light is the conversion factor between space and time. 1 second of time is equivalent to 299,492,458 meters of space, in the same way that $1 is equivalent to a certain number of euros. They're different units for measuring something that is, at a fundamental level, the same thing. When Einstein combined space and time into space-time, the speed of light became the constant that glues them together. And it appears everywhere in the equations of physics, not because light is special, but because space-time is structured in a particular way. The speed of light is, in a sense, the speed of space-time. It's the speed at which the fabric of reality propagates. And this is why it's the speed limit. Not because light is fast, but because the geometry of space-time doesn't allow signals to travel faster. Any signal, whether it's a photon or a gravitational wave or a neutrino, which travel very close to the speed of light but not quite at it, is constrained by the geometry it's traveling through. And that geometry says, you shall not exceed c. But the geometry itself can change. That's general relativity. The metric, the thing that tells you what distances mean and what time means, can evolve. It can expand. And when it does, the distances between things can increase faster than c, without any signal exceeding c. It's not a loophole, it's a feature. The universe's expansion is built into the same framework that gives us the speed limit. They're not in conflict. They're two aspects of the same physics. I think this is one of the most elegant ideas in all of science. The same theory that says nothing can travel faster than light also says space can expand faster than light. And there's no contradiction, because the two statements are about different things. One is about motion through space. The other is about the expansion of space itself. And the distinction, once you see it, is perfectly clear. It's just that it requires you to let go of the intuitive picture where space is a fixed stage and things move around on it. In reality, the stage itself is alive. It breathes, it stretches. It has its own dynamics, governed by the equations of general relativity. And during inflation, those dynamics went into overdrive. For a brief, extraordinary moment, the stage expanded faster than any of the actors on it could ever move. And when it settled down, the universe was left smooth, flat, seeded with quantum fluctuations, and ready to begin the long, slow process of building everything, all without breaking a single law. You know, there's something I keep coming back to as I think about all of this. It's the sheer improbability of us being here, able to understand any of it. Think about the chain of events. Quantum fluctuations in a field we can't identify, stretched by an expansion we can barely comprehend, seeding density variations in a plasma hotter than anything we can create on Earth, which then collapsed under gravity over billions of years to form galaxies, stars, planets, and eventually a species of primate smart enough to figure all of this out. Every step in that chain is physics. Every step obeys the laws of nature. And yet the end result? A conscious being lying in the dark, pondering the origin of the universe, feels like something that shouldn't be possible. Not because it violates any law, but because the sheer complexity of it, the number of things that had to go right, the precision of the initial conditions, the billions of years of patient cosmic evolution, it all seems too much. And yet, here you are. A collection of atoms, forged in the hearts of stars, organized by billions of years of chemistry and biology, contemplating the very processes that made your existence possible. Carl Sagan said it best, "We are a way for the cosmos to know itself." And tonight, the cosmos is knowing itself through you. Let me tell you about one more beautiful connection between inflation and the universe you experience every day. It has to do with the question of why the universe is so big. I mean, think about it. Why is the universe so incredibly, absurdly, mind-bogglingly large? The observable universe alone is 93 billion light-years across. That's a number so large that it loses all meaning. You can say the words, but you can't really feel them. And the full universe, the part beyond what we can see, may be vastly larger still. And the answer, at least in part, is inflation. Before inflation, the universe might have been tiny, perhaps fantastically tiny, smaller than a proton. But inflation expanded it by a factor so enormous that what was once microscopically small became cosmically vast. The universe is big because inflation made it big. It's that simple and that profound. And inflation didn't just make the universe big. It made it smooth, flat, and full of the seeds of structure. It took a tiny, quantum, chaotic patch and turned it into a vast, regular, structured cosmos. Inflation is, in a sense, the cosmic sculptor. It took the raw material of the quantum vacuum and shaped it into the universe we inhabit. Now, I want to take a moment to appreciate something about the people who figured this out. Because the story of inflation isn't just a story about the universe, it's a story about human beings. Alan Guth was a struggling postdoc when he had his breakthrough. He didn't have a permanent job. He was worried about his career. And one night, working late, scribbling in a notebook, he realized something that would fundamentally change our understanding of the cosmos. He later wrote that the feeling of that night, the rush of understanding, the sense that something profound had clicked into place, was unlike anything else he'd ever experienced. Andre Linde, working behind the Iron Curtain, without access to the latest Western journals, independently developed his own version of inflation. He did it with sheer brilliance and determination, working in intellectual isolation, driven by the conviction that the universe had to make sense. Georges Lemaitre, decades earlier, proposed the expanding universe and the primeval atom while working as a priest and physicist in Belgium. He was ignored, dismissed, even ridiculed by Einstein himself, and he turned out to be right about nearly everything. Arno Penzias and Robert Wilson, trying to calibrate an antenna, stumbled onto the echo of creation itself. They didn't know what they'd found. They thought it was pigeon droppings. And yet what they detected was the oldest light in the universe, carrying information about the first moments of cosmic history. These are human stories, stories of persistence, curiosity, doubt, and eventual understanding. The universe doesn't care about our struggles. It does what it does, following its equations, expanding and cooling and evolving. But we care. We're the ones who find it beautiful. We're the ones who stay up late and fill notebooks and argue at conferences and check each other's math, and sometimes get it wrong, and sometimes get it spectacularly right. Physics is a human enterprise. And the fact that human beings, these fragile, short-lived, emotional creatures, can figure out what happened in the first trillionth of a trillionth of a trillionth of a second after the beginning of time is itself one of the most remarkable things about the universe. It didn't have to be comprehensible. It didn't have to yield to our equations. But it does. And that's a gift. So let me bring us toward the end of this journey. Let me come back to where we started. Why did the universe once expand faster than light? Because space itself was expanding, driven by the repulsive gravitational effect of a quantum field in a high-energy state. And why didn't that break any law? Because Einstein's speed limit applies to objects moving through space, not to the expansion of space itself. The equations of general relativity allow it. The equations demand it, under the right conditions, and for a tiny sliver of time, those conditions existed. But the answer is richer and stranger than that one-sentence version. It involves the curvature of space-time and what it means for space to be dynamic rather than static. It involves the quantum fluctuations that became galaxies and the cosmic microwave background that still bathes us in the afterglow of creation. It involves a fudge factor that Einstein called a blunder and that turned out to be dark energy. It involves the observable universe, vast beyond comprehension, which may be an infinitesimal bubble in something even vaster. It involves the Hubble tension and the search for primordial gravitational waves and the possibility of a multiverse, and the identity of the inflaton, and the origin of the arrow of time. The answer to the question is simple. Space expanded, not objects. The appreciation of that answer requires the whole journey we've taken tonight. And here's the thing that I hope stays with you. The universe obeys rules. Every single thing that has ever happened, from the first fluctuation of the inflaton field to the light hitting your eyes right now, follows the laws of physics. There are no exceptions. There are no miracles. There are only the equations, playing out across space and time with perfect consistency. But the rules are not simple. They're subtle, profound, and full of surprises. The same equations that give us the speed of light also give us the expansion of space. The same physics that governs the inside of an atom also shapes the large-scale structure of the cosmos. The rules are few, but their consequences are infinite. And the universe they create is a place of staggering beauty, a place where quantum noise becomes galaxies, where the geometry of space-time gives rise to gravity and the expansion of the cosmos, where a field nobody has ever directly observed drove the most dramatic event in cosmic history, where the leftover heat from the birth of everything still fills every corner of the sky, whispering to anyone patient enough to listen. You're lying in that universe right now. The atoms in your body were forged in the cores of stars that lived and died billions of years ago. The electrons in your neurons are obeying quantum mechanics this very moment. The gravity holding you against your bed is the curvature of space-time, bent by the mass of the Earth. And the space between the galaxies is expanding, gently, quietly, carrying the universe into its future. The speed of light is unbroken, the laws are intact, and the universe continues to expand, as it has since the very beginning, carrying everything with it into an ever larger, ever cooler, ever quieter future. And you're here for it, right now, in this particular moment, in this particular universe, in this particular arrangement of atoms that somehow learned to wonder about itself. That's a pretty good thing to fall asleep to. So let your mind settle. Let the ideas we've talked about drift and swirl, like stars in a slowly spinning galaxy. The speed of light, the expansion of space, the inflaton field, the cosmic microwave background, the quantum fluctuations that became everything. You don't need to hold on to all of it. That's the beautiful thing. The universe holds on to it for you. The laws keep running. The expansion keeps going. The light keeps traveling. And tomorrow night, or the night after, or some night when you're looking up at the stars and wondering, the universe will still be there, doing its thing, following its equations, expanding and evolving, and being exactly as strange and beautiful as it has been since the very beginning. Rest easy. The universe has it from here. And if you dream tonight, maybe dream about space stretching out in every direction, carrying the galaxies along like boats on a rising tide. Dream about a universe that was once smaller than an atom and is now vast beyond imagining. Dream about photons that have been traveling for 13 billion years and are just now arriving at your eyes. Dream about how all of this, every bit of it, happened without breaking a single law. And that, in the end, might be the most remarkable thing of all. Not that the universe expanded faster than light, not that inflation happened, not that quantum fluctuations became galaxies, but that all of it, every moment, every expansion, every fluctuation, every star, every atom, every thought you've ever had, is consistent, lawful, comprehensible. The universe makes sense, not easily, not obviously, but deeply, profoundly, and the fact that you can understand it, even a little, even just what we've talked about tonight, means that you and the universe share something, a language, a logic, a way of being that connects the very small to the very large, the very old to the very new, the laws of physics to the experience of lying here in the dark, breathing, thinking, drifting. Sleep well. The universe is expanding. The laws are holding. And somewhere, right now, a photon that left a star 13 billion years ago is making its final approach toward Earth. It's been traveling since before the sun existed, before the Milky Way existed in its current form, since the universe was young and hot and full of promise. And when it arrives, it won't break any speed limits either. Good night.